I'm Dr. Marion Martin, and I know chemistry. Physical chemistry is a sub-discipline of chemistry where we use light to study matter. And the reason why we can do that is because different chemicals absorb different wavelengths or different energies of light. And so we can use that to identify what chemical is present. We can use that to determine how much of a chemical is present. And we can also use that to look at the structure of the chemical that may be present. In my research group, we're using this in particular to study how different polymers are grown. And so when I say polymer, that's just where we link one compound to itself many times. So an example of a polymer is going to be a plastic material. And we're developing polymers that can be used for bionic devices. So again, with a bionic device, we have one component of that is going to be biologically compatible, and then the other component is going to be electronically conductive. So again, the term bionic combines biological with electronic devices. An example of a bionic device would be the cochlear ear implant. And one of the problems with these devices is that, again, you want it to be biologically compatible and also have electronic connectivity. We want the body to accept that ear implant as being part of the body and not reject it, say, causing swelling or inflammation that is a negative response to the presence of that implant. And so one way to do that is to have a biologically compatible component in the polymer. And so when we introduce that to the body says, oh, this is not a problem. I don't need to send my defense mechanisms to try to defeat or remove this foreign body, but instead it's going to accept the polymer coated metal as accepted in the body and not lead to inflammation, which is a problem with current implant technologies. And so in our lab, what we're doing is studying these polymer composites where we're taking something from algae, so that's where we get our biological component, and we're combining it with a polymer that is electronically conductive, and so that's where we have this electronic device. When we develop these polymers, we have two methods of trying to study the physical characteristics of the polymer. The first is an optical tensiometer, which allows us to study how water is going to interact with that polymer film. So if we have a system that's just glass or metal, when we put water on that system, the water just spreads out because that surface is what we call hydrophilic or water loving. And so in that case, the water just spreads on it. Whereas if we were to put a polymer film on that surface, that would make that film hydrophobic. And that means that the water fears that surface, and that means that the water is going to beat up on itself. So an example from everyday life would be either Rain-X or say car wax, where you put the car wax on your car, and now that water is going to beat up instead of just running off of the car. In our particular cases, when we're putting the polymer on the metal surface, we'll take a measurement before and after we introduce the polymer. And so before, the metal surface should be hydrophilic, and so the water will spread out, and then after it'll be hydrophobic, and we'll get a nice water bead on the surface. And we can make measurements of what is called the contact angle, and that's just the angle between the water bead and the surface. And then as that angle changes between the water bead and the surface, then you're going to go from a hydrophilic to hydrophobic, and we can characterize whether or not we've introduced our polymer to that surface. The second example of how we study these polymer films is an infrared technique. So again, I talked earlier about using light in order to study different compounds. And so depending on that light, we can get almost a fingerprint for each molecule that's present. And so by using this infrared technique, I can identify what chemical is present, and then we can also look at the different structures associated with that polymer. And so by combining both the contact angle measurement, where I'm trying to determine whether or not the polymer is present, and then also I can use the IR technique to identify the structural characteristics of that polymer, and then we can go from first identifying what's present and then using it in a different system in order to understand how the structural characteristics impact the functionality of the polymer. I'm Marion Martin, and I know surface chemistry. We have obtained these polymers from one of my colleagues here at Furman University, and my colleague looks at how changing the synthesis of the polymers is going to impact the structure of the polymer, which is then going to impact the functionality of the polymer. So let me define some of those terms. So when I say synthesis, that is the series of steps that are taken to create the polymer or to create the molecule. So you start off with some starting material that may involve a component of your polymer, and then you'll have a series of, say, 5 to 10 steps that are followed in a specific order in order to create the polymer. And as we go along with that synthesis, you can change different parameters in that synthesis, which is then going to impact the structure of the polymer, and then ultimately the structure of the polymer should impact the functionality or the uses that are available for that polymer. And so the optical tensiometer as well as the IR spectrometer are techniques that we then are able to use to characterize those polymers. And so if we change the synthesis parameters, then we would expect the optical tensiometer's contact angle measurements and the IR spectrometer measurements to change when we change those synthesis parameters. And as a result of that, we can track how changing the synthesis has impacted the structure, and then we'll take the polymers and then go do further testing to look at how the functionality has changed, because we expect there to be a relationship between the structure of the polymers and their functionality or their uses for chemistry. I'm Dr. Marion Martin, and I know chemistry. Well, I can trace my interest in chemistry back to when I was, say, in the 4th or 5th grade. I had an older brother, and for Christmas he got a chemistry set, and we used to play around with the chemistry set, and so that kind of sparked my interest in science and in chemistry. And then when I got to high school, I really enjoyed calculus. I really enjoyed chemistry. Was able to take advanced placement chemistry, and that again really spurred my interest in chemistry. And then also I was able to do a research project, which is not something that's common for high school students, but I was able to do a research project which allowed me to work on my own, studying these different chemicals and how if I changed the metal present in a complex, it would change the color, which is, I guess I'm giving a simplified version of that, but it was just really interesting to me that if I changed how I was synthesizing these materials, I could change the colors associated with those materials. And so from there, when I graduated from high school, I knew I wanted to major in chemistry when I came to Furman University. And at that time, I wasn't sure exactly what I wanted to do. I thought about maybe teaching high school chemistry, or as I spent more time at Furman, my professors encouraged me to think about getting a PhD in chemistry. And as a student at Furman, I was able to do summer research and just really being able to do more research and really understanding what it is a scientist and a chemist does. It's not just mixing chemicals together, but also being able to solve problems. With my interest in physical chemistry, there's a lot of physics and a lot of math associated with that. And so I could see how all these things were coming together to allow us to study the world around us and to make technological advances to improve society. So that encouraged me then to go on and get a PhD in chemistry, where I went out to California and went to Stanford University and did research in physical chemistry. And then after doing research for 2 years in Southern California, I came back to Furman University, where now I'm an assistant professor. Most of my days are spent lecturing and preparing for lectures, but I also have a research lab where I do research with students. And I was really excited about coming back to Furman because it's an opportunity for me to kind of give back the same experience that I had at Furman, where I enjoyed being in the classroom, but getting into a laboratory and being able to do experiments on my own and with my advisor, Lon Knight, really spurred my interest in chemistry, and it has brought me back here to Furman University.